The next thing we want to look at is the planet Mars. And here you see a photograph of Mars, and it doesn't look that dissimilar from Earth. This could be some desert on Earth. If I told you this was a photograph of somewhere out in Nevada or something, you probably would have no reason to disbelieve me. It doesn't seem particularly alien, but yet it is. This is a whole nother world, and this photograph, I believe, was taken by one of the probes that we've sent to Mars. We've sent many probes to Mars to explore its surface, and you see here desolation, but also beauty. It's really kind of a pretty picture. Now here we see a picture of the orbit of Earth and compared with the orbit of Mars. And remember, Kepler's law tells us that the orbits of the planets are ellipses with the sun at one focus, but if you look at the Earth's orbit, it's pretty close to being circular. It's a little bit smushed out, but it's much closer to a circular orbit than the orbit of Mars. You can see that Mars is more eccentric in its orbit. It's more smushed. Not the sun is a little bit offset from the center, more so in Mars, and that affects the amount of sunlight reaching it because sometimes it's closer to the sun, sometimes it's further away from the sun. Because its orbit is not perfectly circular, it's not always the same distance from the sun. And this next slide is showing that because of the eccentricity of Mars's orbit, that sometimes it's much further away from the Earth and sometimes it gets much closer to the Earth. And so we can see here at this location that the distance between the Earth and Mars is about 0.37 AU. Remember, AU, that stands for astronomical unit. That's the average distance from the Earth to the Sun. So here the distance between the Earth and Mars is about a third of the way of the distance from the Earth to the Sun. Whereas when Earth and Mars are at this part of the orbit, the distance between the orbit of Mars and the orbit of the Earth is much larger. Here we see it's about 0.58 or about 6/10 of an AU, so it's much further away. Okay, here we can see some of the physical properties of Mars. One thing that we can note is that the radius of Mars is much, much smaller than the radius of the Earth, and the mass of Mars is much smaller than the mass of the Earth. Remember, the mass of the Earth had 10 to the 24, this is 10 to the 23rd, and that's actually another typo. We can fix that. That's 10 to the 23rd there, and that means 1 with 23 zeros following after it. The density is also much less. We can see that that's different. The length of the Martian day, however, is very similar to the length of the Earth day. It's a little bit more than 24 hours, but a day on Mars is about the same time as a day on Earth. So that's kind of cool, that similarity. Now, from Earth, we can see that on Mars there are these polar ice caps that grow and shrink with the seasons. And we can see some images from Mars missions where the images were taken from probes that were closer up, and we can see a lot more detail on the planet. And again, just to remind you, these pictures have this little legend here, and that V is highlighted, indicating that these are all pictures taken with a camera looking at visible light, the kind of light that we're able to see. So this is not like a infrared image or anything like that. This is actually what Mars looks like. Now, the changing polar ice caps, the reason that they change, you probably know that on Earth, in the Arctic, that there are long periods of darkness that last for months, and then there are long periods where the poles are getting sunlight. And so when the northern pole is fully illuminated, the southern pole is in darkness, and vice versa. Well, something similar happens on Mars, and so there are long periods of time where the poles are in darkness, and it cools significantly, and the carbon dioxide in the atmosphere basically freezes into dry ice. And so frozen carbon dioxide is called dry ice because even on Earth, it doesn't ever go to a liquid stage. You know, regular water ice on Earth, it goes from solid to liquid as you heat it up, and then it goes from liquid to steam as you continue to heat it up. So it goes from solid to liquid and then liquid to gas. On Mars, because the Martian atmospheric pressure is so low, dry ice and water ice behave the same way. They don't really form a liquid state, or they don't stay liquid very long. They tend to go directly from solid to gas. And what happens in the winter of a particular Martian pole, the dry ice coalesces and forms on top of the polar ice caps. And so typically what you have is you have these huge polar ice caps that are made of water ice that are covered by dry ice, which is, of course, frozen carbon dioxide. And, of course, during the summer months, the sunlight is evident on the poles and it's heating up these ice caps. And so these top layers of carbon dioxide that are frozen, they tend to, turn into gas and they sort of float away. And so the ice caps on Mars are changing. The southern ice cap actually has a much higher or much thicker layer of dry ice, and so it doesn't change as much as it does in the northern pole. But that's sort of what we see. These ice caps, they have these huge amounts, gigantic amounts of water ice that are covered by this layer of frozen carbon dioxide. Now, some other observations of Mars is that Mars has frequent dust storms, and we can see that here in this third bullet point. There are huge dust storms on Mars, and they have very, very high winds. And this causes a shifting dust cover on the surface of Mars, so looking at Mars from day to day, week to week, month to month, year to year, the surface features seem to change because you have this shifting dust cover. Now, one of the major features on the Martian surface is called the Tharsis Bulge. This is a huge volcanic plateau in the western hemisphere near the equator, and it covers about a quarter of the surface of the planet. This region contains Olympus Mons, Olympus Mons is the tallest mountain in our solar system. And actually, Olympus Mons is a volcano, which we believe last erupted about 25 million years ago. But it is an absolutely gigantic surface feature. Also featured in this region is the Valles Marineris, which is a system of canyons that runs along the surface in the Tharsis region. It's more than 4,000 kilometers long. It's about 200 kilometers wide and about 7 kilometers deep. It is an absolutely gigantic, massive canyon system, vastly larger than the Grand Canyon on Earth, and one of the largest canyon systems in the solar system. Another feature of this region is that it has very minimal cratering, and that means that it's a younger surface. Now, what do we mean when we say that fewer craters is indicative of a younger surface? Well, you might remember we talked about how early in the history of our solar system there was this period called the Great Bombardment Period, where there were many, many collisions, many things were just pummeling the planets. Comets and asteroids and meteors and all these things were smashing together. And we see evidence of that, and we see all these craters. So we talk, for example, about the cratering on the moon. And so we still see those craters on the moon that happened millions, even billions of years ago, because the moon's not geologically active. There's no erosion, there's no tectonic activity on the moon, there's nothing to change those surface features or erode them away. So we say that that's an old surface because it hasn't changed in a long time. But if the surface of a planet is active, like the Earth's surface, those craters, they tend to get covered up by erosion, by motion of different things. And so younger surfaces show fewer craters, typically speaking. And so when we say that there's minimal cratering in this region, and that indicates that the surface is younger here on Mars, that's what we're talking about. Now, previously we've seen sort of the map of the Earth and the map of Venus, and here is a map of Mars. And again, you can see that the colors here are indicative of elevation, not the presence of water or something else. And so you can see the areas where it's blue mean that the elevation is lower. The elevation where it's yellow is kind of the normal, and where it's white indicates that you've risen up. So you can see, for example, the white in the Tharsis Bulge region, you can see that there is a elevation there because it's higher up. Here you can see the canyon we just talked about, the Valles Marineris, which is, you can see that it's yellow and orange surrounding it, but it's blue here, indicating that that's a deep impression. And so that's that deep canyon that we talked about. And different regions are lower or higher depending on their surface features. You can see that one of the nice things here that we see are some of the landing sites of different probes. We can see here is where the Spirit probe landed, where Curiosity, Opportunity, the Viking probe, Viking 1, Viking 2, the Pathfinder probe. These are different spots where we've been able to directly investigate by having literal boots on the ground, or I should say probes on the ground. But the geology and the geography of the planet are really interesting, and we can see how they compare and contrast to the Earth. So when we look at some of the features of the Martian surface itself, we see that the northern hemisphere, which we can see indicated on the left, is this sort of rolling volcanic terrain, and the southern hemisphere, which is indicated on the right in the picture, is heavily cratered. There are a lot of highlands, and the interesting thing is the average altitude is about 5 kilometers above the northern hemisphere. We saw in the previous slide that the northern hemisphere had a lot of blue in it, indicating that it was depressed, it was sunken in compared to the southern hemisphere. One of the other things here we can see, if I look at the picture on the left, which is the northern hemisphere, we see it's a lot smoother. We don't see these cratering features, which suggests that the northern surface is a lot younger than the southern surface. So maybe it was subjected to more erosion, and that means probably that the northern hemisphere must have been lowered in elevation and then flooded with lava to sort of cover up those features. Now here is the Valles Marineris, the giant canyon that I talked about a little bit ago. It's 4,000 kilometers long. Its maximum width is 120 kilometers. It tends to, not always be at the maximum. It's about 7 kilometers deep, as we've talked about. Here we can see this little box here has been blown up, and so you can really see those features. And for contrast, you can see this little inset picture. That's showing the Grand Canyon on Earth. And so you guys are familiar with the Grand Canyon, which is this huge canyon on the Earth, and to the same scale, you can barely even notice that there's a canyon there. It's so small compared to the Valles Marineris, which is this gigantic canyon on the surface of Mars. People that have gone to the Grand Canyon and looked out across it, and they've just been inspired by its breathtaking beauty. I've often wondered, what it would be like to be on the surface of Mars looking over the Valles Marineris. I think it would be an absolutely breathtaking sight in terms of its beauty and its majesty. Now, this is the Olympus Mons volcano that we talked about. It's the largest volcano in our solar system. Now, one of the things that's interesting, it doesn't look like a typical volcano. It's so big in diameter. And so you can see from one side to the other side, it's actually 700 kilometers across in its diameter, and it's 25 kilometers high. So you could start climbing this volcano, and the elevation is so gradual, you wouldn't even necessarily realize that you were climbing a mountain or climbing a volcano, but you would just keep going and keep getting higher and higher and higher, and you would actually go up 25 kilometers high by the time you got to the summit. So that is a gigantic feature. One of the big questions that we are very interested in is the question of whether or not there is water on the surface of Mars. Now, we know that there are in the polar ice caps large amounts of water ice, but we're really interested in the possibility of liquid water existing on the surface of Mars, because sometimes the temperature of Mars does get high enough that you could possibly have liquid water on the surface. Now, unfortunately, because the pressure of the Martian atmosphere is so incredibly low that liquid water cannot stay on the surface very long. It just will evaporate into the atmosphere. But if it existed in Mars's past, there could have been maybe oceans on the surface of Mars. There could have been rivers and things a long, long time ago before the atmosphere eroded away. And maybe there are places where the water is buried underground or something where you still have, if not on the surface directly, near the surface of Mars, you might have large water features. And that's important because one of the fundamental questions that we want to know is there any life on Mars? Now, we're not talking about little green men, but maybe something like bacteria or something akin to very, very simple life that exists on Earth. Maybe that still survives on Mars. Maybe many, many millions of years ago, when Mars was more Earth-like, when it had liquid water on its surface, there may have been, some life, even possibly life of relative complexity. And does any of that survive? Does any evidence of that survive? That's an open question. Could there even be life today still existent on Mars? Right now, we don't have any evidence that that's true, but we haven't been able to go there ourselves. We've only been able to send these little robots there, and so maybe they just haven't found it yet. But right now, it's still an open question. But it's an important question because we've talked about how that is one of the big questions in astronomy. Are we alone? Is there anyone else out there? And, the only place we know of really that life has ever managed to take hold is our own planet, the Earth. But if life managed to take hold on Mars, independently of the Earth, life that didn't come from the Earth, but life that independently evolved on Mars, or anywhere else in our solar system that we find, that would suggest to us that life is plentiful, life is everywhere. And maybe it would suggest that we're not alone, that there must be someone else out there. But if there is no life on Mars, if there is no life anywhere else in the solar system but Earth, that might suggest to us that maybe we are alone. Of course, neither way is going to be a proof, but it is a question that gives you another data point if you ever get that answer. Now, on the surface of Mars, we do see some features that suggest the presence of liquid water. So, for example, in this figure on the left, we see these runoff channels that resemble sort of the delta structures that exist around rivers on the Earth. As I said, we believe that there was once significant water on the surface of Mars. There was a catastrophic flood that occurred about 3 billion years ago. We see features in the geology of Mars that suggest the presence of former liquid water. And here's another image. Again, it looks like a delta on Earth, and so this may be an ancient Martian river delta. And so maybe a long time ago on Mars there was water. And of course that's important because water is one of the key ingredients for life. On Earth, wherever you have liquid water, you have life. And so That's why we think that, the presence of water on Mars is something we're searching for. Because if we are going to find life existing on Mars, it's probably going to be someplace where we find liquid water. And so, does liquid water exist on Mars anywhere? It's an open question. But this video is getting pretty long, so we're going to make this a good stopping point, and we'll carry this on in the next video.